The primary visual cortex, V1, Part 3, Simple cells and complex cells. So far, we have spoken about V1 neurons' tunings to input features such as orientation, scale, color, motion direction, disparity, as if the neurons are linear, with a filter or kernel K. But in fact, V1 neural responses are very nonlinear functions of visual inputs. A character is to treat V1 neurons as if each belongs to just one of these two classes, simple cells and complex cells. Simple cells have static nonlinearity so that in many respects one can approximate them as linear. So if we denote the outcome of this linear operation as L, then the response or outcome O from simple cells follows a static nonlinear function of this L. When we ignore the spontaneous firing rate, which is usually near zero in V1 neurons, this is a typical depiction of such a nonlinearity for a neural response O along vertical axis versus the linear outcome L along the horizontal axis. Qualitatively, there is a rectification nonlinearity and there is a saturation nonlinearity. So therefore, just to examine the preferred features of a simple cell, such as orientation, scale, color, motion direction, disparity, and preferred spatial location, which is just the residual location, then the neuron can be treated as if it is just linear. Information in this negative L region is not signaled by this simple cell. This information can be signaled by a second simple cell neuron whose residual filter in its linear part is the negative of that of the first simple cell neuron. So for example, if the first neuron has this filter, this neuron prefers a black bar, then this will be the filter for the complementary second simple cell neuron, preferring a white bar. Each on or off region in the original filter becomes an off or on region, respectively. So, two such complementary simple cells can act as a group, as a whole simple cell that is more linear, and this is often used as a model for simple cells for convenience. A complex cell is not well described by a static nonlinear function of the linear outcome L. An energy model is often adequate to describe it as receiving inputs from a pair of two simple cells. Now let's focus on space for simplicity. These are the Gabor filters K1 and K2 for the two simple cells. They are such that they have a 90-degree phase difference. So here one is written as a cosine, the other as a sine function with phase psi. For example, when this phase psi equal to 0, one is a bar detector preferring a white bar and the other is an edge detector. If we are given a visual input grating with frequency k and phase phi, these are the linear filter outcomes L1 and L2. Each one is sensitive to this phase difference. This means these L1 and L2 depend on how the on and off regions of the filters match the peaks and troughs of the input grating. For example, this would be a good match with this off region to a black grating stripe and its on region to a white grating stripe to give a high response, but this would be a poor match. Of course, the responses increase with the match between the grating frequency K and the preferred frequency K hat by the Gabor filters. To get the complex cells response, first these linear responses L1 and L2 are squared before they are added up to give this complex cells response, as if it is an energy value from these two simple cell components. Then we get this response value to the grating. And this response value does not depend on the phase phi of the grating. And this means that it does not depend on how the darker and lighter stripes of the grating are aligned with any particular on or off region of the two underlying simple cell filters, K1 and K2. This pair of simple cell components is called a quadrature pair because the two filters are 90 degrees from each other in the phases of their Gabor filter constructions. If the input is a bar rather than a grating, one can show that the response from this complex cell will also be insensitive to the exact location of this bar. Whether this bar is aligned with any subregion of the filter does not matter too much. The bar could also be here or another location, as long as it is more or less within the Gaussian envelope of the two Gabor filters. Let's say that this bar is at a distance x0 from the center of the Gaussian envelope, and the center of the Gaussian envelope is also the center of the resistive field of this complex cell. Then the complex cell's response is roughly this for a bar whose width roughly matches the width of the on and off regions. This response is also insensitive to whether the bar is black or white, so you can put a white bar, it's also okay, because this squaring operation removes the sign of the original linear dependence. So in summary, a complex cell is insensitive to small spatial variations and the contrast polarity of the visual inputs. Here is a complex cell to signal motion direction of visual inputs and described by a motion energy model. Recall that a linear cell tuned to motion direction is a filter oriented in space-time. When we have a quadrature pair of such filters, and then we square their linear outcomes and sum them up, the result is motion energy. It describes a complex cell's response tuned to direction of motion of visual inputs, and this response is not overly sensitive to the exact spatial details of the moving inputs within the resistive field. Here is a disparity energy model for a complex cell from two simple cell components. For the first simple cell, these are the two Gabor filters for the resistive fields, one for the left eye and the other one for the right eye. For example, they could appear like these. These two filters have the same location for their Gaussian envelopes, but they differ in phases parameterized by XL for the left eye and XR for the right eye filter. And they correspond to the peak horizontal locations for the filters. So these two Gabor filters have different shapes, but this simple cell has this preferred phase difference. Now this is for the second simple cell and their Gabor filter shapes. These two simple cell components differ by 90 degrees in phase, so the cosines become the sines. Now XL and XR correspond to these locations for black to white transitions in the Gabor filters. So this simple cell has the same preferred phase difference as the simple cell above. Now let the first simple cell have linear response L1 to visual input, and the second neuron has linear response L2, and then they are both squared to give the energy response to visual inputs. Now, when visual input has disparity D, this is roughly the response. This response is maximum when the input disparity is equal to the preferred disparity XL minus XR. And this disparity tuning in this complex cell neuron is not overly sensitive to the exact spatial details of visual inputs within the overall resistive field envelope of this neuron.